Hello everyone, welcome to Pharmacochemistry classroom. Here I am with a very important topic, that is nucleophilic substitution reaction or SN reactions. They are divided into SN1 and SN2 reactions. Details. We will see what is the definition. So first we should understand what is substitution. Substitution implies that one group replaces another. So this is a simple word meaning of substitution. Our topic is nucleophilic substitution. So what is nucleophilic substitution? Nucleophilic substitution is a substitution reaction of an electron pair donor with an electron pair acceptor. So here an electron pair donor come and get substituted on an electron pair acceptor. Electron pair donor is a nucleophile, which are negatively charged and having electrons to donate. Now we will see the requirement for a substitution nucleophilic reaction to take place. That is general components of a SN reaction. First is substrate, second the leaving group, third nucleophile, fourth the solvent. Now we will see each component in detail. First is substrate. In a reaction, the reactant on which the particular reaction takes place is known as substrate. So for our substitution nucleophilic reaction, an alkyl halide is a substrate. So alkyl halide is the substrate on which the substitution takes place. They are alkyl molecules in which halogen has replaced a hydrogen. There are different types of alkyl halides. You can see here methyl halide, primary alkyl halide, secondary and tertiary. So alkyl halide is a substrate on which SN reaction takes place. Halogen atom in an alkyl halide is often denoted by symbol X. Next is leaving group. From a substrate, a group leaves, that is known as leaving group. Leaving groups, here you can see an example. So look at this. This is our alkyl halide substrate. From that leaving group, that is halogen atom, leaves. This group or this halogen on the alkyl halide is a leaving group. Now how the leaving groups are formed? Leaving groups are formed by heterolytic bond cleavage between carbon and halogen. And after this bond cleavage, this halogen atom takes the electron pair with it. Here you can see the order or how strong the leaving groups are. Here, weakest base is the best leaving group. Now what is this weakest base meaning? Lowest base. Lowest base are those which can donate its electron pair to any electron acceptor. So here you can see the arrangement of fluoride, chloride, bromide and iodide, and out of this iodide is the weakest base and that is the best leaving group. Next component is nucleophile. Nucleophile, I told already, nucleophile is nucleus loving species. They are having negative charge and they can donate a pair of electron to any electron acceptor. See here, this is an alkyl halide on which substitution is going to take place, and this OH minus is a nucleophile. When heterocyclic fission, when heterolytic fission take place, this leaving group, as we have seen in the last slide, leaves the substrate and making this as an electron acceptor or a positively charged or partially positively charged species on which this nucleophile can come and attack. Here are some examples for neutral nucleophiles and charged nucleophiles. Water, ammonia, amines, etc. are given in the case of as an example for neutral nucleophile. Charged nucleophiles, RO minus, NH2 minus, RNH minus, etc. Next component is solvents. Solvents are used in SN reaction to dissolve the reactants and to facilitate the reaction. Protic and aprotic solvents are used in SN reaction, and their details we will see in factors affecting SN reaction. We have seen the components required for SN reaction. Now we will see the details of the SN reaction. Here you can see a general reaction given. In that, our alkyl halide substrate is present, and this is a nucleophile which come and attach on this, and you get a substituted product. You can see here nucleophile is attached on this R group. So a substituted product, and here the leaving group. Based on the bond making and bond breaking and the number of molecules involved, there are two types of SN reaction. They are SN1 reaction and SN2 reaction. We'll see SN2 reaction now. SN2, as we all know, S stands for substitution, N for nucleophilic, and 2 for bimolecular. So the reaction is bimolecular. That is, the rate of the reaction depends on both the reactants. What are the reactants here? One is alkyl halide and another one is nucleophile. Therefore, the kinetics followed by SN2 reaction is second order kinetics. So you can see here, rate is equal to K into concentration of alkyl halide and concentration of nucleophile. Now we will see the mechanism of SN2 reaction, which was proposed by Hughes and Ingold. The reaction takes place in a single step, that is, the bond breaking between the leaving group and attachment of nucleophile on the substrate takes place in a single step. That is why this SN2 reaction is a single step reaction. Now you can see there is a transition state formed. That is, when the nucleophile approaches the substrate, the bond between the carbon and the nucleophile forms. At the same time, the carbon and leaving group bond breaks. Therefore, in the transition state, there is a partially formed bond between carbon and nucleophile, and there is a partially broken bond between carbon and leaving group. Eventually, the bond between the carbon and nucleophile forms firmly and the leaving group leaves the substrate. So, we get the substituted product here. So, hope you understand the mechanism behind SN2 SN2 reaction is a single step reaction in which the bond between the leaving group and carbon breaks and nucleophile comes and attaches the substrate in a single step, which gives a transition state having 5 groups attached to the carbon. You can see here partially broken bond between the carbon and leaving group and partially formed bond between carbon and nucleophile, and the other 3 atoms attached. Total 5 groups are attached in the on the carbon in this transition state, and eventually the bond between carbon and nucleophile form firmly and leaving group leaves the substrate and we get a substituted product. This is the mechanism. And here we have seen this is a transition state. You must remember what is a transition state formed in SN2 reaction. This is a species in which 5 groups attached on the carbon atom. Here you can see properly, this is the leaving group. It leaves eventually, and this is a nucleophile which came and they form a bond, proper bond between the carbon and this nucleophile to get a substituted product. Next is about the stereochemistry. We know that bond breaking and bond making takes place in a single step. So what happened? This nucleophile comes and attached on the carbon to the face opposite to the leaving group. That is why we get a product which has a configuration which is opposite to that of our starting material, because the attachment take place opposite to the leaving group. So there is inversion in configuration happen in SN2 reaction, which is known as Walden inversion. Next, how fast or what are the substrate which undergo SN2 reaction? Methyl primary alkyl halides undergo SN2 reaction with easily. Methyl and primary alkyl halide undergo reaction very easily. Secondary alkyl halides slowly, and in tertiary alkyl halides the reaction will not take place. And what is the reason? The reason is steric hindrance, because the more bulkier groups are present on the carbon bearing leaving group, it is very difficult for nucleophile to come and attach. That you can see here. This clearly explains if the steric hindrance is increasing, the nucleophile cannot come and attach on the alkyl halide. Here there is no steric hindrance. Nucleophile can directly come and attach on the carbon bearing alkyl halide, on the carbon bearing halogen, and here it is somewhat okay, but here it is very difficult because there are bulkier groups attached on tertiary alkyl halide. So SN2 reaction is not possible. Increasing number of R groups on the carbon atom decreases the rate of SN2 reaction. Unhindered alkyl halides like methyl halides, primary alkyl halides undergo the reaction very easily. Next we will see the energy diagram of our reaction. What is the energy diagram? This is a graphical representation showing relative potential energy of reactants, transition state and product as a reaction progresses with time. So here you can see our reaction. Our reaction is SN2 reaction. Here the energy in this y-axis and reaction coordinate here in the x-axis. So here you can see, always remember a stable product have lesser energy than its transition state and the reactants. So here you can see that reactant has an energy. Here, as the reaction proceeds, it gets converted into a transition state which has more energy than the reactant, and it will come down to the product having lesser energy. So we all know that any system has more energy in it is unstable. So obviously we know that our transition state is unstable, which immediately gives the product. Now here you can see few examples where alkyl halide reacts with a nucleophile and get a substituted product. Here we will summarize the points we have seen in SN2 reaction. First is kinetics, it follows the second order kinetics, and the rate of the reaction depends on two molecules, that is why it is known as bimolecular reaction. And what are the molecules? First one is alkyl halide, second is nucleophile. Mechanism follows one-step reaction. Stereochemistry, which involves Walden inversion due to the backside attack of nucleophile. And ease of reaction, unhindered halides react faster, that is why methyl halides and primary alkyl halides react easily, and tertiary alkyl halides will not undergo SN2 reaction easily. Next we are going to see SN1 reaction, that is substitution nucleophilic unimolecular reaction. This is a unimolecular reaction. Here the rate depends on only one reactant, that is alkyl halide. The kinetics followed by SN1 reaction is first order kinetics, that is rate is directly proportional to the concentration of alkyl halide. Next comes the mechanism of SN1 reaction. The reaction takes place in two steps. SN1 reaction takes place in two steps. What are the steps? The step 1 is a formation of carbocation. First step in SN1 reaction is a formation of carbocation. The leaving group leaves the substrate and we get a positively charged carbocation. See here, the leaving group leaves and a carbocation formed. After the formation of the carbocation, next step is the attack of nucleophile on the formed carbocation. The step look like this. See here, these two are the carbocations, and on this carbocation, since they are planar in nature, nucleophile can come and attach either from left side and to get a substituted product here, or from the right side to get another substituted product. So the product formed in SN1 reaction is a racemic mixture. Next we'll see about the transition state present in SN1 reaction. We have seen the transition state is the carbocation. What is carbocation? It is a species containing carbon having a positive charge and which is attached to other three bonds, and they are formally known as carbon cations. There are different types of carbocations. You can see here primary, secondary and tertiary. Tertiary carbocations are more stable one because it has methyl more number of alkyl group attached to it. These alkyl groups can donate electron to the positively charged carbon here and can stabilize this tertiary carbocation. More number of alkyl group attached, more stable the carbocation becomes. That is the reason why tertiary alkyl halides undergo SN1 reaction, because they give stable tertiary carbocation. Next we will see the stereochemistry of SN1 reaction. Stereochemistry of SN1 reaction can be explained by examining the geometry of the carbocation intermediate. So look at here, the carbocation formed here. See this. This is a carbocation formed, and here this carbocation containing other three atoms or group of atoms attached to the carbon containing positive charge and has a vacant p orbital which is located above and below the plane. That is why the carbon atom is sp2 hybridized state and they are trigonal planar having the p orbital above and below the plane. So, the nucleophile comes and attach from either left side or from the right side because they are planar and it is easy for them to come either through this or through this side to get the product. Here the product you can see they are having configuration opposite to each other. So this mixture of product formed gives a racemic mixture. Next about the rate or the ease of SN1 reaction. I told already tertiary alkyl halides undergo SN1 reaction easily because they gives the most stable carbocation intermediate. The more stable the intermediate is, more easily the reaction take place. Now we'll see the energy diagram of SN1 reaction. We have already seen what is the meaning of energy diagram. So look at here. The substrate tertiary alkyl halide which gives a carbocation which is stable through this high energy transition state. So once this transition state formed, very immediately we get a carbocation which is our intermediate, and on that this nucleophile come and attach and get a transition state 2 which will give you the stable substituted product. So these are the representations on this energy diagram. Next we will see the characteristic of SN1 reaction. Just like SN2 reaction, here the kinetics, it follows first order kinetic. Rate is directly proportional to the concentration of alkyl halide alone. Nucleophile has no effect in the rate of the reaction. Mechanism follows two steps. First one is the formation of carbocation. Next is the attack of nucleophile on the carbocation. Stereochemistry is based on the geometry of carbocation. So we will get a racemic mixture as a product, and the rate at which or the ease of SN1 reaction is more substituted halides react fastest, and this is the order of SN1 reaction. That is tertiary alkyl halides react faster, then secondary, then primary, then methyl halides have very least reactivity towards SN1 reaction. Now there is a trick to remember SN1 SN2 reaction. You will never forget if you remember SN1 SN2 reaction using this method. So this is an illustration by talented Canadian political cartoonist Graham Mackay, so that we can use this to explain our SN1 and SN2 reaction. Look at here. This is alkyl halide having a leaving group, a black cat, and here the nucleophile. So look at here. As soon as the leaving group leaves, there forms a carbocation. On that our nucleophile can come and attach to get a substituted product, that is SN1 reaction. So I hope you understood, and here the same illustration will take this alkyl halide, on that this black cat which can leave present or it is sleeping on that, and the nucleophile which can come and sleep on this comfy chair is waiting. But now what happened? No more waiting, because it is a SN2 reaction. Bond breaking and bond making takes place in a single step. So this will come and break the bond between this leaving group and the alkyl halide, and this nucleophile gets substituted on that, so that you get a substituted product. This story or this illustration will help you to remember SN1 SN2 reaction always. Here we are going to compare SN reactions. Here in first column SN2, second is SN1 reaction. And the first difference is here in SN2 reaction, rate depends on alkyl halide and nucleophile, and thus it's a bimolecular reaction. And here rate depends upon alkyl halide alone, nucleophile has no effect on SN1 reaction, so it's a unimolecular. Rate, this is what I explained just now, rate is equal to K into alkyl halides concentration into nucleophile concentration. Here rate is directly proportional to only alkyl halide concentration. It has only one step, SN2 has only one step, SN1 has two-step reaction, and transition state is unstable intermediate in SN2 reaction, and in SN1 reaction they are carbocations and they are stable because tertiary alkyl halides undergo SN1 reaction easily. And here ease of formation or ease of reaction depends on the steric hindrance. That is why the primary alkyl halide which has least steric hindrance follow SN2 reaction when compared to secondary and tertiary. Here ease of the reaction depends on the stability of carbocation. That is why tertiary carbocations which are having more stable carbocations will undergo SN1 reaction. Tertiary alkyl halides undergo SN1 reaction compared to secondary and primary. When it comes to stereochemistry, we have seen in SN2 reaction Walden inversion present, and in SN1 reaction we get racemic mixture as product. Some possible questions from this topic. First thing is the definition of SN1 and SN2 reaction. Then write about their mechanism, kinetics and stereochemistry. Second possible question, why tertiary alkyl halides do not undergo SN2 reaction? And comparison of SN1 and SN2 reaction. Thank you. Hope it helped you. Please like, share and subscribe and keep watching Pharmacochemistry Classroom.